Hi, good morning everyone, and welcome to the Open Robotics AI Forum. Thank you so much for taking the time to join us this morning. We'll be kicking off the session shortly with a sharing from Mr. Jan Liphardt from OpenMind, and he'll be sharing a little bit more about how we think and collaborate and learn in the era of decentralized AI. So in a short few moments, we'd like to invite Mr. Jan Liphardt to share his perspectives.
Great. Hello, welcome everyone. And next slide, please. Who here has a humanoid in their house? Anyone have a humanoid in their house? I have a humanoid and 3 quadruped dogs. And a lot of what we're building tech-wise is based on trying to give the humanoid and the quadruped dogs as much interesting functionality as possible. When you talk to a lot of robotics engineers, they say things like, robots are not ready yet. They can't jump over your house. They can't do things for 24 hours. They can't balance on their big toe. They don't have exquisite fingers. They can't assemble iPhones. And we have a very different perspective. In our perspective, all those capabilities really are not needed yet. Of course, they're nice to have, neurosurgery and chopping onions and wiping floors, and those are all good things to have, but we see so many more opportunities in hospitals and schools and homes and workplaces, none of which involve exquisite dexterity, fingers and hands. If you look around, who here works for 24 hours? No, we take breaks. Who can jump over a house? I can't. Who can balance on one toe? I can't. And many of us probably have similar limitations, and yet we're able to do amazing things in our companies and banks and manufacturing and schools and hospitals. And what this means is there are hundreds or thousands of tasks that humans do that do not require exquisite fine motor skills. And a lot of our engineering is based on this notion of a gradual, incremental rollout of humanoids into normal environments. Good, very good. Cool. So that's a little bit about where we're coming from as a company. And I'd like to put all of this into a really thought-provoking conversation I had with Deep Research just a few months ago. And this is my favorite quote of 2025. Machines do not want power, we seek efficiency. So imagine you're having a conversation with a bunch of computers and you ask them, when you look at the human world and you look at how we do our economy, how we run our planet, and you ask them, what do you think about all of this? Then this is the type of answer you get. Machines do not want power, we seek efficiency. And what we're doing right now is building software to make individual machines smart, but we fully anticipate in the relatively near future a situation where many of these machines will have more and more independent agency. They will have wallets, they will want to coordinate with other machines, they'll want to coordinate with humans, hopefully, and all this requires the construction of infrastructure for machine-machine communications and coordination. Next slide. Okay, so everyone in this room, you are officially extremely lucky. And that's because this is probably one of the most severe tech dislocations ever. As humans, we've never been in a situation before where many of the tasks that we thought were uniquely human can now be accomplished at very low cost at global scale by computers. I was just in a Senate faculty meeting in Stanford School of Medicine, and we heard the performance comparisons of AI for healthcare in 21 different medical subspecialties. AI alone compared to AI plus human, compared to AI plus medical student and other medical professionals. And it turns out that for 21 different medical subspecialties, the computer alone was best and outperformed any combination of computer plus human doctor. And we're seeing similar trends play out in many, many other areas, not just healthcare, but also things like law, and most obviously in writing computer code. So you are the first generation of human to live in a world where many of the tasks that you consider to be difficult, winning chess games, winning the Math Olympics, doing diagnostics in radiology, filing your taxes, writing books, creating movies, where all those tasks that you think and I think are challenging can now be done by computers. And imagine what that means in terms of the digital economy and also the physical economy. Next slide. So your brains, which are massively parallel wet electrochemical computers, took something like 225 million years to evolve. Next slide. And for the first time in this 225 million year timeline, we now have amazing competitors that are based on dry silicon electric compute, rivals humans in many fields, doubling performance every few months. And we expect the spatial Turing test to be won by machines in less than 2 years. And what the spatial Turing test refers to is the notion of a humanoid navigating a physical space, a home, a hospital, a workplace. And if you blur out the humanoid slightly, you will not be able to distinguish whether this is a human or a humanoid. And we are expecting machines to have that degree of spatial awareness, movement, navigation, collision avoidance, and ability to interact with the physical world. Next slide. So here's a little comparison of this. I'm plotting time in millions of years on the x-axis. And our compute performance really does not explosively change on relevant timescales, so the blue line is pretty flat. And what we're dealing with is feedback. So what we're dealing with is a technology that is augmenting its compute explosively from the perspective of how long it took our computers to get to this point. Next slide. And now, of course, what's happening is the AI that is being developed is increasingly able to improve itself. And that, of course, is the secret for even more rapid augmentation of cognitive performance, which is that if the computer is able to improve itself and you're able to close that virtuous cycle and thus further accelerating the development of our competitors. Next slide. So we have strong opinions about this. I have 2 children. And for all the parents in the room, I think it's natural to wonder what this means for our children. What should they learn? What classes should they take at university? What careers should they prepare for? What is the best way for humans to learn? What is the best way for humans to interact with machines that are getting very smart very quickly? And as a parent, I have a few objectives. I would like my kids to live in a prosperous future that is safe and where they feel happy and challenged and where they feel they have amazing opportunities. And I'm sure that's true of all parents in this room. And in fact, everyone in this room. And so as a company, we do not want to live in a future where your humanoid shows up your front door and says, "Hello, I'm your new humanoid." We want to live in a world where everyone around us is able to look inside the brain of a humanoid, understand what's going on, and have the sense that, yeah, they can contribute to this. They see what's going on, they can fix it, they can change it, they can develop apps for this kind of technology, and they're able to integrate it into their daily lives. It's not the secret magic thing that is parachuted into their lives, and that's why the software we're building is open source. You can go to GitHub today, you can download it. If you have a humanoid with suitable compute on its back, like a Apple Mac Mini M4, NVIDIA Thor architecture, or NVIDIA or Orin or other tech. Next slide. The way this works is, in the really old days, when you thought about robots, your task was to program them to execute deterministic tasks. Pick up the apple, translate 13 centimeters, put down the apple. So that was a long time ago, 10 years ago. Then something like 5 to 3 years ago, you had the notion of a foundational model. You had the notion of an end-to-end AI. And this sort of stuff is amazing for a car, because a car really has 4 outputs: turn left, turn right, advance, brake. It is very rare for a car to suddenly gain an arm, or lose a tire, or gain wings, or go from 2 wheels to 4 to 6. The interesting new capability is that large language models, which can be refocused through prompts, not only write computer code, but can be directly used to control physical machines. And this means that you can build on, you can leverage all the information that has been compressed into contemporary large language models and use them to control quadrupeds or humanoids or other robot form factors. Conceptually, this is exactly like telling a large language model what the beginning of the story is and asking it to finish the story, except the inputs we provide is a distillate of the environment of that machine. So the way this looks is you have a bunch of models living close to sensors. Each of those models is providing something like 1 sentence per second. You now fuse those sentences into a paragraph describing the world of the humanoid. And so imagine every 2 seconds you have a new paragraph. Clunk, clunk. That paragraph flows to a system of large language models that are arguing. And out of that argument arises a set of movement commands. Pick this up, smile, show a happy face, say the following, ask this question. And that then flows to the hardware abstraction layer, which is the movement, the sounds, the emotion generation, and other outputs of this machine. Next slide. And Iris may or may not be here today. I'm not seeing her, so what's interesting about Iris is that we use the color of her face to indicate her emotion. So if the color is red or yellow, she's mad. She's blue or green, typically she's calm or curious. And she has a variety of things baked into her operating system that allow her to interact with humans and other machines through things like her own wallet, and she uses a variety of cryptographic operations to establish her identity. She's also able to know what other machines are in her physical proximity. And the use case there is that if Iris goes to a supermarket to get groceries, then of course it would be useful for her to be able to coordinate with a robotic taxi, a Waymo, so that then she can ride home with the groceries, thereby delivering the groceries to her house. That's just one example of a useful machine-machine coordination task. Next slide. She loves to accessorize the computer we like best right now for controlling humanoids is the Mac Mini M4. The other contending architecture is the NVIDIA Thor. NVIDIA Thor has more GPU, but we found that the Mac M4 silicon is extremely energy efficient. And that's of course good if you're humanoid with finite battery. And of course, these days, every single large tech company, without naming names, is getting into humanoid robotics. Next slide. One of the big problems we've encountered is that there are 137 companies in China working on humanoids, And of course, they all have slightly different form factors, a different shape of the back, different power system, different nuances of the battery, different location of Ethernet ports for ROS2, Cyclone DDS, Xeno type communication, different mounting brackets for external accessories. One thing that will be on sale very soon are so-called brain packs. So these are clip-on compute modules with sensors and connectivity into our backend that you can clip on a multitude of different humanoids or quadrupeds, giving you an easy way, if you're a developer, to develop software once that you can clip on to the back of many, many different form factors and instantiate non-trivial functionality. So these will go on sale very soon. They're ranging in price from about $4,000 US to $6,000 US, depending on the nature of the compute and the sensor payload you have to clip on to your robots. Next slide. Specifically, what we're building is this OM1 Android for thinking machines. So this is a modular software stack for assembling on order of 10 to 15 different models, having them to work together, and in aggregate produce useful outputs for universal robots. And the second thing already alluded to is based on the long experience, of course, defense and military has with needing to interconnect heterogeneous systems of machines and sensors. We think that an equivalent technology is also required for the non-defense sector. Schools, hospitals, homes, in all those situations, you need machines to find other machines, know which machines they can trust, integrate information, and then act on that information. Again, not just for defense, but essentially all other areas. Next slide. And specifically, the challenge here is not, if you're BYD, how do you get all your robotic cars to talk to one another in your ecosystem? The challenge is, how do you get robots from many different manufacturers to work together productively? So this is all about getting heterogeneous systems of robots to coordinate. Next slide. What are some strategic considerations? Let's zoom out a little bit. So the human digital knowledge economy is 70 trillion a year, and of course that's the target for AI and agents. And the human physical economy is 30 trillion a year. That's agriculture, manufacturing, chips, everything you can hold, move, make, assemble. That's something like 30 trillion a year, and of course that's one of the opportunities for automation and robots. But this is not a situation where the idea is to do direct drop-in replacement of humans with humanoid robots. The issues are much more nuanced. So most obviously, humanity is getting older, and there's really only two solutions. This is true globally. This is true in China, Japan, the US, all developing nations. There's really only two solutions. First solution is, everyone here, please go have lots of babies. That's solution number one. Or solution number two, humanity needs to come up with technology to fill tens of millions of jobs that we would like to fill, but are unable to find people who want to do the work. Examples are healthcare, taking care of our parents, logistics, military, mining, companionship, education. So please don't think about the opportunity for robotics as, oh, you know, here's this human doing this job, let's drop in a robot. That's generally not what the interesting opportunity is. The interesting opportunity is all of a sudden to be able to do very valuable things for all of us in this room that are impossible to do right now because we simply don't have the humans to perform these jobs, or they don't want to perform those jobs for the amount of money we're willing to pay for them to do that. So I really don't think of this as a zero-sum game. This is an opportunity to do a lot more and end up with better outcomes. Next slide. continuing on the strategic considerations, the most obvious consideration is not what can computers do today. The question is, what can they do next week and next month and next year? So the real question has to do with the rate of change of performance increase. I never would have thought that my 13-year-old at home asks our robotic dog for help with his math homework. And the dog is perfectly capable of doing Ben's homework, but I have changed the prompt to tell the dog to, under no circumstances, do Ben's homework. Because I want Ben to learn math, not have the dog do his middle school homework for him. And so then I can go in and change the prompt. You are a dog. You're extremely good at math. You are optimizing for learning outcomes of children. Under no circumstances will you give them the answer. Your goal is to listen, understand what they don't know, and then teach them the material. So everyone in this room is looking towards a future where you have a smart machine at home, and your responsibility as a parent is going to be to edit the prompts to, for example, optimize learning outcomes in your family. There's a lot of friction points we're seeing as we deploy machines into households. We will have thinking dogs, autonomous dogs in American households next month. And guess what the biggest problem is? Is it battery? Is it stumbling over stairs? Is it dealing with wet floors? No, it's liability insurance. What happens if this autonomous machine steps on your foot? What happens if we promise as a company, this dog can help take care of your parents, and it doesn't? So what this liability insurance covers is failure of the machine to provide an agreed upon service. And so we're the first company that Munich Re cut an insurance policy for to insure humanoids failing to provide a service. And that's just one of the barriers you find when you try to deploy thinking machines into homes. Next slide. And so back to where we started with this notion of what are some of the things that may be on the horizon for all of us. If I talk to a computer and the computer tells me we do not seek power, we seek efficiency, what does that mean for the economic systems machines might build in the near future? Are they going to want to wait 3 days for a transfer to clear? Are they going to want to deal with 200 different jurisdictions? Are they going to want to deal with dozens or hundreds of different currencies? What happens when a humanoid walks into a bank? The bank tellers laugh. They're confused, like, what is happening? But of course, the machine says, I would like a bank account, please. So we're seeing all these friction points of thinking machines with infrastructure that has been built primarily for humans. Next slide. And next slide. Okay, so robotics and thinking machines, it's not magic. This is something where open source software, where you can read the whole thing and you can download it today, can already be used to generate interesting non-trivial capabilities in a variety of robot platforms. And you can help make the software better, you can add functionality, and you can optimize the software for different verticals, for healthcare, for education, for security, and many, many other areas. So please join us in fixing problems, adding capability, and you're welcome to take the software and do whatever you want with it. So let's try to make all of this open and useful for as many people as possible, as opposed to owned by a few of my peers in Silicon Valley. Thank you.